Looking at worksheet A here for chapter 11, starting off with number 3. So we got sector of a circle. It's also talking about arc length. So one thing we gotta slide that over real quick. Sorry. One thing we gotta consider for these are the formulas. They're going to be really popular in this chapter. So let me just point you to those real quick, and we'll write them down so we have them. So we got arc length is the angle times the radius. So arc length is the angle, always in radians, times the radius. So these guys are always done in radians. And then you got your area of the sector. So we got the 1/2 times the angle times the radius squared. So I'm just writing this down real quick so we got them for the rest of our problems. So, all right, so we got those two formulas now. So we're given a couple things here. We're given an area of 1, and we also know the length of the arc is 2, and we're just finding the radius and the angle. So based on what we know so far, let's just plug in our information. So we know the area was 1, so I can plug in a 1 right there. So one of my equations, I got 1 equals my 1/2 theta r squared. And then on the other one, we were told the length is 2, so I also know that 2 equals that. So obviously we got two unknowns here. We're solving a little system of equations, so we can use some substitution. So one thing to recognize is the angle is 2 over the radius, or you could say the radius is 2 over the angle, but one of those we need to do and then sub in. So I'm going to get the angle by itself, so I know that 2 over the radius is theta. So if I plug that in onto my other equation, so I'm now replacing my angle with 2 over the radius times r squared. So just a little cleanup on that. I can multiply 2 over to the left. I also have my 2 on the right, so I guess I could have just divided right there, but I also got my 2 on the right. R squared over r is just r, so I divide the 2 over, and I have my radius of 1. And now I can just take that back in, obviously, and plug it into either equation to get my angle. So if I put a 1 right there and divide that over to the other side, and obviously 2 divided by 1 is 2, so oops. So there's our angle for that one. Always in radians. So we always, these formulas, whenever you plug in angles into those guys, we always plug them in radians. So if you ever had degrees, convert them to radians first before plugging them into those formulas. Moving on, number 4. So we got an isosceles triangle with a perimeter of 36. And the value of the cosine of each angle is 1/5. Alright, so we're looking for an area, and they're giving us a specific form in which to write our answer. So this is very specific, so we got to make sure our answer comes out looking like this, where a is a number that we're going to figure out here, and they're just telling us that a is an element of the natural number system, which is just like 0, 1, 2, 3, 4, 5, and so on. So anyway, let's start out with what would help with a little drawing on this one. So we have an isosceles triangle, which means my left and right sides are equal, and the base is something else. So one of the things they tell us here is that the perimeter is 36. So I know these sides add up to 36. We don't know exactly what those are yet, so let me come back to that. The value of the cosine of each angle is 1 to 5. So let me draw in the height for this to create those right triangles so that I can use my cosine function. So they're saying the cosine of any angle, so we're just going to use this angle for now. So the cosine of that angle is 1 to 5. So for this, remember, cosine is adjacent over hypotenuse. So we know the relationship is 1 to 5. We don't know what the actual numbers are, so we're just going to put some x's in there. So it's 1 times something and 5 times something is that relationship. So that's how we're making use of that. Remember, this is isosceles, so this must also be 5x. In an isosceles triangle, the height does cut the base in half. So that would also be a 1x right there. And so now we can use the idea of a perimeter of 36. So if I add all those up, 5x plus 5x plus 1x plus 1x, if I add all those up, I get 12x. And we're told the perimeter was 36. So now we know the x value is 3. So now I could plug those in and actually work with some real numbers. So I got those are 3's and those are 5 times 3, which is going to make them 15 each. So if you notice, we do have that 1 to 5 relationship within the numbers that we're working with. So as far as the area of the triangle, we could just do a 1/2 base times height. So on this one, we know the base right here, the total base would be 2x. And as far as the height on this, we do a little Pythagorean theorem to get the height. So if I do a little, a squared plus b squared equals c squared, I can get the height. So with my 3 and the 15, we got to use that to get the height of the triangle. So let me do that off to the side. So I got my a squared plus b squared is equaling c squared. So 225 minus 9 is going to give me 216. So when we square root, remember what we saw earlier on in this question. It's giving us a very specific format for our answers. So I'm going to simplify this radical. So if I can see the square root of 216 as 36 times 6, and I can put that in simplest radical form. So we know the square root of 36 is 6. I got that 6 left over. So there's the format I'm going to put in there for the b value, which is the height. So I should have put a 6 right there. That would have made more sense. But anyway, here's kind of what we got. So we already know that total base was 6 once we figured out those real numbers. So anyway, if we do a little cleanup on that for what we now have, half of 6 is 3. 3 times 6 is 18. And then I got the rad 6 behind it. So there we go. And we formatted the answer in the way that they said to format it. We figured out the a value was the 6, which doesn't really matter. What was important was that we formatted our answer to look like their answer. So so we know we answered that in the proper way. All right, moving on to number 9. So we got a quadrilateral over here at the right. So find the length of AC. One thing to keep in mind for AC is within the whole drawing, you have a non-right triangle and a right triangle. So keep that in mind. So whenever we're dealing with the non-right triangle side, that's things like the sine rule, cosine rule, those types of things. But if you got the right triangle, then we're going back to some basic trig and Pythagorean theorem on that side. So and in order to come up with AC, we don't have enough information on the right triangle, so we have to use the non-right triangle to get the length of AC. So it looks like we got the cosine rule for this one to come up with AC. So remember, if that's angle B, that would be side B. So you can either call that little b or you can call it AC, whatever works for you. So we're going to use cosine rule on this one. So we got our AC squared So there we go. Sorry. So there's our setup with the cosine rule in order to get AC. So obviously all that's going into a calculator. It is in degrees. So make sure at this point your calculator is in degrees. They're going to square root both sides in order to get AC. And if we did that right, looks like AC comes out to be about 13.3. Good rule of thumb is to put those things into your diagram once you find them. Sounds simple, I know, but that might help you as you kind of move forward within the question. So we now got the value for AC. So now they're asking us for the angle CAD. Sorry, so CAD. So we're now looking for this angle right here. And now for this one, notice that's part of the right triangle. So now you're just back into basic right triangle stuff. In a right triangle, that is the opposite leg, and that is the hypotenuse. And so we know sine, and just think of SOHCAHTOA, sine is the one that does opposite over hypotenuse. So we can say the sine of angle CAD is equal to opposite over hypotenuse. And so anytime you're trying to find an angle, that means to use an inverse function. So again, make sure you're in degrees for this problem. So, but if I did the inverse sine of 5.4 over 13.3, we get the size of our angle. So 3 sig figs, we'd have to say about 24.0, correct to 3 sig figs. Moving on, number 13. So right here, let me slide down. So triangle ABC, we have a we have a non-right triangle. So again, we're thinking back to sine rule, cosine rule, and the non-right triangle stuff. All right, so angle BAC is obtuse. That's important because remember there's certain cases where you can get angles that could sort of be that ambiguous case, and so they're telling us specifically that it's an obtuse angle. So that's something we got to make sure we take note of and read carefully. Always on a test question, you got to read for little things like that because that can cause you to miss points. So we know the area, we know AB is 9, we got this is 12, so find the size of angle BAC. So with this one, they did give us an area. So remember, the area of a non-right triangle is 1/2 AB sine C. So 1/2 the side times the sine of the included angle, which is the angle between those sides. So I got my 1/2 AB sine C. So let me just call that A for this one. And we know that equals 27. So just doing a little solving here for A, at the end of which we're going to have to do an inverse function to get the angle. So if I take this, let's see, 54. So if I take my 54 and divide it over, so we know sine A is 27 over 54, which is 1/2. So you could use a little trig function if you remember your unit circle type stuff on something like this. The sine of what angle has a value of 1/2. So you could kind of use some unit circle knowledge on that one if you wanted to. We can also just do a little punch into the calculator for this. So if I did the inverse sine of 1/2, right, we have our 30-degree angle. So here's something I want you to keep in mind though. If you had a 30-degree angle, so that would be this guy right here. So with a 30-degree angle, remember in a sine function, the sine is like your y value. So we're going up and down, which means the sine where you would get 30 is the same value as this angle right here. Right? Those guys are the same sine function because they both go up the certain amount, the same amount. So these guys are going to have the same sine function. So where you would have 30 degrees, you would also have 150 degrees. So in this one in particular, either answer would fit. So it could either be 30 or 150. This one specifically said it was obtuse. So I had to take the 150 as my answer because it does say obtuse. Moving on. Number 16. So we got the center of a circle, a radius of 5.4. We're in radians right now. So the area of the shaded sector is 32.4. Find the length of minor arc AB. So we're looking for arc length. Remember we talked about those little formulas earlier on. So you got arc length, which is the angle, times the radius in radians. So one of the things we already got for this is the radius. So I already know there's a 5.4 going in for this. I need to figure out the angle measure that I'm working with. And what they gave me for that is the area. So I got to use the area to get the angle so that I can come up with my arc length that I'm looking for. So again, we already know the radius was 5.4. So we got to figure out that angle so that I can get my arc length. So the area of the sector that we saw earlier, that's your 1/2 theta r squared. Again, we already know the radius is 5.4. And in this case, they also told us the area was 32.4, so I can plug that in for the area, and now I can just use that information to get my angle. Once I know my angle, I can plug that in to get my arc length. So just some simple math on that. You got your 5.4 squared. That's going into the 32.4. And then times 2 to get the angle by itself. And let's write that as a fraction. So 20 over 9 is my angle. So that can now go in. So I just multiply that by 5.4 and I have my arc length. So moving on to number 19. So D is the base of that vertical pole. Let me slide this down. So D lies on AC. A and C are 88.5 meters apart. So keep that in mind. We got AC is 88.5. Angle BAC is 18. Always good to fill that stuff in. BCA is 33. So calculate the length of BD. So ultimately this is what we're looking for right here. Again, we also know AC was 88.5, so keep that in mind too. So a little tricky on this one because it's like we almost have enough information to use a little right triangle trig to get BD, but we don't know how this 88.5 is broken up amongst this segment and this segment. We only know the total. So we're just going to say this much of it is X. So this must be 88.5 minus X. So just to represent it with something so that we can start using some trig functions. Let me start with angle A. So remember, we're solving for BD, so we want to include him. From here, he is the opposite leg. That's the adjacent leg. So if we say tangent of 18 equals the opposite over the adjacent, then that means if I multiply this over to the left, I have a function for BD. So we can now say that BD is equal to 88.5 minus X times the tangent of 18 which, you could obviously put that into your calculator and distribute it if you want to do that. So you could do that at any point. If you want to do that now, that would be fine. If you wanted to do a little cleanup, let me just show you where the other function is coming from angle C. We know the tangent of 33. Put that right over here. Is equal to opposite over adjacent. So if I multiply the X over to the left, I now have another function for BD, which says it is X times tan 33. And so I got two functions for BD. If both of those functions equal BD, then by substitution they equal each other as well. So I can now set this equal to this and then just solve for X algebraically. So now I have my 88.5 and that's going to equal my X tan 33. And this is, at this point, you would need to punch these guys into a calculator, make sure you're in degrees to get some real numbers out of those. And then you just get X by itself. That's all you got to do at that point. So put that in, distribute it, and then same thing. Put that in your calculator, and now just get X by itself algebraically. So moving on to 22. So now we're dealing with some boats moving from the same point. So one boat moves in a straight line at 24 kilometers per hour. Other boat 36. So the angle between them is 75. Find the distance between the boats after 3.5 hours. So you got one boat taking off. That one, the angle between them is 75, so let me kind of approximate that as best as I can for a 75-degree angle. Ultimately, we are trying to find the distance between the boats. So let me call that one X. So the first one is 24 kilometers per hour for 3.5 hours. So we're doing this 3.5 times. So you got your 24 times 3.5 in order to get that distance. And then on the other one, the other guy's moving at 36 for 3.5 hours. So we can use that to get his distance. And then now it's just a basic cosine function, cosine rule function to solve for x. So you got your x squared. So a squared, let me get some real numbers for those. So instead of the way it's written right now, I got 24 times 3.5. So that's really a length of 84. And on the other one, 36 times 3.5 is a length of 126. So a squared equals b squared plus c squared minus 2bc cosine A. So there you go. That's the full setup right there. Just put that into a calculator. Should be in degrees. And then at the end, make sure you do square root it in order to get x by itself, but that should be your distance. So let's move on here to 23. All right. So 23, we got triangle OAB. Right angle triangle, we got a couple sides on that. Obviously, we could get this when we want to with Pythagorean theorem, or if you recognize that this is 6, 6, 6 rad 2 based on 45, 45, 90 rules. But anyway, talking about a couple arcs and some centers for those. So calculate the area of sector OACB. So looking for area of this sector right here, which is that entire piece. So of course for that we're just using the area of a sector, so area equals 1/2 the angle. So remember that's 90 degrees, but it has to go in radians, so we got to convert from 90 degrees into radians. So if you don't remember the basics on that, you should know that it's pi over 2, but if you didn't, you can just take your angle times pi over 180 in order to convert it. So that's always an option too. So the angle on that one is pi over 2. And then for the radius on that one, since we're centered at O, the radius is simply 6. Or 6 squared, there we go. So a little cleanup on that. So 6 squared is 36 divided by 4, which is 9. So we can leave that in terms of pi. Better to be exact. So moving on, area of segment ACBP. So ACBP. That doesn't seem right. So that must have said sector. So I think they were intending for that to be sector, not segment. So so they're looking for this part right here. So for that sector. So again, we already know this entire piece is 9 pi. So if we just subtract out the triangle from that, that's going to leave me with this shaded part. So I'm taking the entire sector and I want to subtract out this right triangle, which is just 1/2 base times height. So just doing 1/2 base times height. It's going to give me this shaded region that they're asking for. So let's see, half of 36 would be 18. So we're just going to write it as 9 pi minus 18. Area of the shaded region, ADBC. So now we're looking at this part right here. So something else to consider. If we can get this entire region and then subtract out this answer from it, that's going to leave me with this shaded part. So that's kind of the overall goal for this one. So we know the entire thing is this. Sorry, we know this shaded part is this. So if I can get this entire piece and subtract out this from it, that's going to give me that shaded part. So I need the entire part of this, which is just half of a circle. So for this one, if I just do half of a circle minus this, that should do it. So for this circle, keep in mind the radius of that circle would be this right here. So since this entire thing would be 6 rad 2, that would make this 3 rad 2. It would just be that part of it. And you could have done that with Pythagorean theorem or 45-45-90 rules. But either way, we get the radius of 3 rad 2. So it's just half of a circle. So I'm going to do 1/2 of pi r squared. So 1/2 pi times that radius squared. So that should be a good setup for us. And then we could probably just leave this in terms of pi. So if I were to square that, so let's see, 18, half of 18 is 9. So that half circle that we have up there is 9 pi. So I got 9 pi minus 9 pi. Remember, this negative would distribute to both of those. So that makes this a plus 18, which is all we are going to be left with on this one. So 18 should be our answer. All right, moving on to 24. So getting into our last two here. All right, 24. So triangle ABC, given some values and given an area, find two possible values for BAC. So let's just draw this one out. Give it a rough sketch just to place some values. So on this one we got AB is 10, AC of 7. We know the area is 21, so find two possible values. So remember, one of our area formulas is 1/2 AB sine C. So in this case, sine A, we would say. So I got my 1/2. I got my 10, 7, and then the sine of the angle between them would be that guy. In this case, we know the answer is 21. So there's our setup. So right here we got 70. Half of 70 is 35. Divide that over, you got 21 over 35. And of course you could reduce that if you wanted to, but it's really not necessary because that's not our answer. Punch that in, inverse sine of 21 over 35. So we got the 36.9 is one possible answer, could be 36.9. This one says two possible answers, so if we also subtract that from 180, we can get the supplement to that. So 180 minus that answer is going to give us our other possible value. So those are the two possible answers for that one. And last one here, so our bearing problem. This one was really nicely already kind of laid out for us, so that really helps. So ship leaving the harbor on a bearing of 325. Remember, that's 325 from the north. So right here, if we're leaving the harbor 325 from the north and travels 30 kilometers to point A. So right here, traveled 30 kilometers. And remember, this is from the north. So from the north, if I go all the way around like this, that was 325. So what does that leave me with for right here? So if I did 360 minus 325, then that tells me this angle is 35 degrees based on that statement. And sorry, that was a 30 right there. So there we go. So at point A, trip stops and resumes on a bearing of 260 from the north. And it's now headed to point B. So we got your 45 right here. So again, keep in mind this is now from the north as 260. So from here all the way to here is 260. So if I did 360 minus 260, I also know this angle is 100. So a couple things we can just be filling in as we go. So we also know that from here, if that is 35 degrees, then this is the supplement to that. These are what we would call consecutive interior angles. So since they're both connected to vertical lines, they must add up to 180. So that's another way we can get some values for this. So we also know this is 145. Knowing those two numbers, we can also figure out this angle. So I also know if that's 245 total, 360 minus 245, tells me this is 115. So just kind of some basic geometry knowledge. You kind of have to put all that together to make sure you're getting all the information that's necessary here. So, so find the distance from H to B. So we are now coming up with that guy right there. So I'm just call that X. So based on the drawing that we have right now, this is a non-right triangle. Just using our basic cosine rule to figure this guy out. So on this one, you got your angle from here. So we're going to start with the x squared. And then you got 45 and 30 are the sides. So that would be our setup, and then just solve that out, take the square root so you can get your value for x. And that's going to answer that question. And then the second ship leaves harbor H to meet the first ship at point B. So it's traveling that distance. So find the bearing of its course. So, so we figured out in the last part this is 63.8. And so in order to get the bearing, we're going to need, remember it's from H, so we're going to need to know this angle right here in order to figure out from here how far it went to get here. So if I can get this angle and subtract it as well as 35 from 360, that can then give me that bearing that we're looking for, which is this guy. So the bearing that it traveled, what we're looking for is ultimately that right there. So we're looking for that angle, so let's subtract out this guy right here in order to figure that out. So I need this angle. So that is angle BHA. So a little sine rule on this one, so we can say 45 over that. Sorry, BHA. And that would equal the sine of 115 over 63.8. So there you go. So do a little cross multiplying on that. Ultimately, you have to do an inverse sine to get that angle. But if we do that part, it looks like we got 39.8 degrees for him. Sorry, this is getting a little clouded over here, but if I take my 360 and subtract out those two angles from 360, that's going to give me my bearing that I'm looking for. So that would be your last step.